In this video, we will discuss Thevenin equivalent circuits, particularly when you are given a dependent voltage source. So some background on Thevenin equivalent circuits is that they're supposed to look like this one here on the bottom right. Of course, you want just a voltage for the whole circuit and an equivalent resistance, but if not, you can solve for another two variables and just apply Ohm's law.
You can use two different methods to find the equivalent circuit. So you can either use source transformation, where you combine all the sources and the resistances, or you can use nodal and or mesh analysis like we will in this video.
So here we will find the Thevenin equivalent circuit seen by RL in the circuit below. On the right here are the particular values you will use. They are a lot more simple than what you will see on a quiz or test, but are good for basic understanding. Usually you would want to short all your voltage sources and open all your current sources, but of course you cannot short a dependent voltage source, so we will do things differently. The first thing we will do is nodal analysis to find the voltage going through RL. So you would have like an almost open wire there. The second thing we will do is mesh analysis, where you will do a short wire going through RL, and this will help you find the current going through RL. And now that you have these two variables, you can use Ohm's law to find the final VTH and RTH you want.
So the first step for using nodal analysis in this video is we'll find the nodal analysis from the bottom node. And so you would subtract the 1 volt source by the dependent source over the resistor that's in between. And then you'd subtract the ground from the dependent source. And since the ground is equal to 0, then you would just have that as 0 over the 2 ohm resistor. Multiplying by the denominators, you can then get your simplified version of the equation. And then combining those, you can get your equivalent current for the dependent source.
So now that you know the I naught and the dependent source value, you can do nodal analysis at the top node. So you will get this first equation. You equate the denominator to be 12 so that you can simplify it into the second equation. Just some simple algebra and plugging in the I naught you found gives you this third equation. So you are able to find VOC.
The first step for finding our mesh analysis is to realize that the path of least resistance in this case, as a result of shorting the RL, makes the dependent source go to 0 since that path is not favored. And since that path is not favored, you can see that the mesh also has I2 equal to the current that you're solving for. And so in the first mesh, you would multiply the resistor by the current in that mesh, and then you would add or subtract the voltage source depending on which direction it's going. And then when you have a resistor that's in between two meshes, you would subtract the current that's going in the opposite direction. And so since the current for the dependent source is equal to 0, you can eliminate that factor and combine the like terms to get your final mesh current.
So similar thing for the second current, you just start here at the bottom, go around in a loop. And of course, the 3A naught is equal to 0. So you just do simple algebra to get the second equation. And then you find I1 in terms of I2 one more time. So now that you have these two equations for I1, you can equate them to each other to solve for I2. Again, to get from this first equation to the second equation here, you get a denominator of 12 on both sides, and simple algebra to give you I2 is equal to 1 over 14 amps. And this is important because you want the ISC, and ISC is equal to I2.
In conclusion, you can use Ohm's law to find the equivalent resistance, which is equal to the voltage divided by the current that you found. And so the equivalent resistance is thus 68 over 19 ohms. And plugging this into the equivalent Thevenin circuit, you can find that the voltage source is 0.256 volts and the resistance is 3.57 ohms.
If it helps you, you could solve this problem in terms of just the resistor variables first and then plug in all the values at the end. And you could also just keep the Thevenin equivalent circuit in fractions instead of in decimals. As you can see here, we have a recap. So on the left is the circuit we solved for, and on the right is its Thevenin equivalent. You can see that they are drastically different. We did use the setup for a Thevenin equivalent seen here on the very right, but there are other ways to draw this, and you can find these other ways online. As you can see, RL is shown in these other configurations, and that is the purpose of a Thevenin equivalent, that you can relate RL to power, or just other functions you might need.